Chapter 3.3, Zeros of Polynomials. Remember, the factor theorem tells us that if the remainder of polynomial division is 0, then we have a factor of our original polynomial. Not only do we have one factor, but both the quotient and divisor are factors. In other words, if we do a division and we get a remainder of 0, then we know that the divisor and the quotient are both factors of the dividend. In this case, 5 and 7 are both factors of 35. So if our remainder is 0, then we have found two factors. We can continue to use synthetic division on the quotient to factor it further. The rational zero theorem tells us that if P over Q is a 0, so if a rational 0 exists, then P will be a factor of the constant term and Q will be a factor of the leading coefficient term. In other words, if we have some polynomial function, if there are rational zeros, P will be a factor of, in this case, -7. So P would be plus or minus 1 and plus or minus 7. And Q would be a factor of the leading coefficient. So plus or minus 1, plus or minus 5. And then possible zeros would be P over Q. So I would take all of these P's, the 1 and the 7, and divide them by 1, and then divide them by 5. So this becomes the only synthetic division that I need to do. I need to take my polynomial up here and divide each one, divide by each one of these values here. Okay? And if I get a 0, then I have found a factor. Okay? Also, some information to help us with finding our factors is that an nth degree polynomial will have n zeros. So this third degree polynomial over here, I would be looking for 3 zeros. A fifth degree polynomial, I'd be looking for 5 zeros. And I know that complex zeros occur in conjugate pairs. In other words, if I is a 0, then negative I is a 0. If 2 plus I is a 0, 2 minus I is a 0. Complex zeros occur in conjugate pairs. Descartes' rule of signs is a theorem that tells us how many of our real zeros are positive and how many are negative. So that is going to help us cut our work down, cut it in half sometimes. Here's what Descartes' rule of signs is. But let's just go down here and practice it. We're going to use Descartes' rule of signs to determine the number of positive, negative, non-real, complex zeros for this equation. The first thing we're going to do is count the number of times that this function for f of x, when I have a positive x in here, changes signs. Okay, so in other words, this coefficient is positive, this one's negative, this one's positive, this one's negative, this one's positive, and this one's positive. So it changed signs from positive to negative one time, from negative to positive, that's the second time, from positive to negative, it changed again, it changes again, but this last time it does not change signs. So this function f of x changed signs 4 times. That means there are 4 or 2 or 0 positive solutions. It's just the crazy thing about Descartes' rule of signs, I'm just always going to go down by 2 until I get to 1 or 0. Now, what I want to do is imagine if I plugged in a negative x in for x. So that would give us 2 times negative x to the 5th minus negative x to the 4th plus negative x cubed minus negative x squared plus negative x plus 5. In other words, plug a negative x in everywhere. Simplifying that, 5 negatives would be negative 2x to the 5th. 4 negatives, this would be positive, but then there's a negative, so negative x to the 4th. 3 negatives is a negative. 2 negatives is positive, but there's another one, so negative x squared plus negative x plus 5. And then count the times this changed signs. Okay, so first we have a negative, and then a negative, another negative, another negative, another negative, and a positive. This only changed signs one time, telling us there is one negative solution. I already am at the 0 or 1, so I don't have to go down by 2. Okay, when we're using Descartes' rule of signs to help us find our zeros, we're really only interested in when it tells us there are no positive or no negative solutions. And then that's going to cut my work in half. I won't have to try any of those positive or negative possible rational zeros. But you might also be asked, just like in this case, to use Descartes' rule of signs to tell us all of the possible kinds of solutions we'll get. One thing we know is there should be 5 zeros. So one thing that can happen is you get 4 positive and 1 negative. Right? That makes my 5 zeros. Or you might have 2 positive and 1 negative, right? Pairing this, but that's only 3 zeros, so my other 2 must be complex. And remember, the complex solutions will always occur in pairs. Or there might be no positive, so 1 negative, and to make the 5 zeros that I must have, 4 complex, or 2 pairs of complex. So using Descartes' rule of signs to tell us the different possibilities. However, we're going to use Descartes' rule of signs mostly to see if we can narrow down our work in trying to find the zeros of these functions. Okay, so here are your steps to find all the zeros. Let's try it for this function. First thing I want to do is try to factor it, but I might notice that if I try to factor out an x squared, and that's going to leave x minus 1 minus 4, which leaves 2x minus 3, it's not going to factor. All right, but try that first, because if I can factor this, I can get all of my zeros in one step. All right, since it didn't factor, I'm going to use the rational zero theorem to list all the possible zeros. That means P will be a factor of 12. So plus or minus 1, 2, 3. I don't know what that is, sorry. 3, 4, 6, or 12. and Q will be factors of the leading coefficient. So in this case, just a 1. So my possible zeros are of the form P over Q, where I'm going to take all of these numbers and divide them by all of these numbers. In this case, I just have a 1, so if I divide all of those by 1, I get the same list, plus or minus 1, 2, 3, 4, 6, and 12. Okay, now I'm going to try to use Descartes' rule of signs to see if I can get some help. So I'm going to look over here and see if this changes signs for just plain f of x. And it goes from positive to negative. I'm through, right, with that one. Let's imagine f of negative x. Now, Descartes' rule of signs is there to save us work. So I don't want to create a bunch of work using this. I'm just going to imagine if I plugged a negative in for every x, that would be negative. Okay, this would remain negative because this would be positive, but I still got a negative. A negative times a negative is a positive. Oh, as soon as it changes signs, then Descartes' rule of sign did not help me with this problem. So I'll go on to my next step then. I'm just going to go down the list and try my synthetic division with each of these possible zeros. When I'm using my synthetic division, double check, make sure it's in descending order, 3, 2, 1, 0, and there aren't any terms missing. And there are not in this one, so I'm going to put up my coefficients. And I'm just going to start with positive 1. Bring down the 1 to get me started. 1 times 1 is 1. 1 times 0 is 0. As soon as I realize this isn't going to be 0, I'm finished. And I'm going to move to my next number in the list. I'm going to try negative 1. Bring down the 1 again. Negative 1 times 1 is negative 1. Negative 1 plus negative 1 is negative 2. Negative 1 times negative 2 is positive 2. Oh, look. Negative 1. Oh, no, I thought I had a 2 over here. Never mind. Negative 1 times negative 6 is positive 6. It's not 0. So I'm just going to move to my next number. 1, negative 1, negative 8, 12. And I'm going to try 2. 2 times 1 is 2. 2 minus 1 is 1. 2 times 1 is 2. Oh, look. 2 times negative 6, negative 12. Yes, now I know that x equals 2 is a 0. X equals 2 is one of my zeros. Not only that, I also now know that x minus 2 times this is going to be an x squared plus x minus 6 are 2 factors. So I couldn't factor that initially, but hey, I just got my 2 factors. Once I get one of my factors worked down to a quadratic equation, I can either continue to factor it, or even if it doesn't factor, I can still find those zeros because I can use this quadratic formula or completing the square. In this case, that thing factors, and it factors pretty easily. 2 numbers that multiply to give negative 6 and add to give positive 1 are positive 3 and negative 2. So here's my other 0. X equals negative 3. And notice x equals 2 occurs twice. So I actually have 3 zeros like I knew we should get, but 2 of them occur twice. This is called multiplicity. And we'll look at the effects of that next time. And no, I don't have to list that x equals 2 twice. As a matter of fact, I probably won't list it twice, but I do see there are 3 zeros. Just one of them has multiplicity. Also, pay attention to your instructions. It could ask you to find the zeros, or it could ask you to use synthetic division to factor the previously unfactorable polynomial. So depending on what your instructions are, the steps to this problem would be exactly the same, but how we leave our answer could look like this or this, depending on if we're trying to find the zeros or factor it. Also notice I have to be told that my instructions are for this problem that I'm finding the zeros. Otherwise, this is a graph, right? If it just says solve this equation, that's going to be a graph because I've got x's and y's that looks something like this. But if it says find the zeros, that means, oh, I'm solving this for when y is 0. And that gets me these x's. All right, let's try that again. All right, how many zeros should we get for this function? Right, 5. I'm looking for 5 zeros this time. Okay, so the first thing I'm going to do is try to factor it. Hey, and I noticed that I can factor an x out. Don't forget, if you can do any factoring, do that right off the bat. Okay, but after that, I can't factor that any further. But I do know if I'm trying to find zeros, and that has to be my instructions, otherwise that'll be a graph, right? But if I'm asked to find the zeros, then I'm trying to solve this equation. Once I have it factored, I know that means, okay, x equals 0, or, remember our zero product property, or the other factor equals zeros. So I've really already found one of my zeros. I'm now trying to find the other 4. Since I can't factor this any further, I'm going to use my P's and Q's, where P would be a factor of 36. So 1, 2, 3, 4, 6, 9, 12, 18, or 36. And Q would be a factor of 2. So 1 or 2. Okay, that means possible zeros are of the form P over Q. I'm going to take all of these numbers and divide them by all of these numbers. Well, when I divide them by 1, it gets me that same list. So first of all, I'm just going to write the list up. Then when I go back and divide them all by 2, I get 1 divided by 2. 2 divided by 2 is already listed. 3 divided by 2 is new. 4 divided by 2 is already on my list. 6 divided by 2 is on my list. 9 divided by 2 is not on my list. 12 divided by 2 is 6. 18 divided by 2 is 9. 36 divided by 2 is 18. Here's all my possible solutions. Oh, I'm really hoping I get some help from Descartes, or think how many possible times I might have to do that synthetic division. So let's go back and look at the original function. Yay, look, plus, 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 plus. It did not change signs. Descartes' rule of signs tells me there are no positive solutions. In other words, it just cut my work in half. I do not have to check any of these positive possible zeros. Cut my work in half. That's awesome. Okay. Make sure, I'm just going to start my synthetic division now. Try to find a zero to send when my remainder is zero, meaning that divides evenly, meaning I have found factors. Before I can do my synthetic division, I can't have any missing exponents, and they have to go in descending order. 4, 3, 2, 1, 0. So just putting up the coefficients, 2, 11, 16, 15, and 36. Let's try -1. I don't have to try +1. Saved myself some work already. -1 times 2, -2. 11 minus 2 is 9. -1 times 9, -9. 16 minus 9 is 7. -1 times 7 is 6. 15 minus 6 is, oh, sorry. Why did I put a 6 there? That's crazy. Okay. I think I was thinking ahead. Okay, 16 minus 9 is 7. -1 times 7 is -7. 15 minus 7 is 8. And I can tell that that's not 0. So I don't really care what it is if it's not 0. Let's go to the next one. Okay, 2, 11, 16, 15, 36. Let's try -2. I don't have to try +2. -2 times 2 is -4. 11 minus 4 is 7. -2 times 7, -14. 16 minus 14, 2. -2 times 2, -4. 15 minus 4, 11. That's -22, so that's not 0. Let's try -3. 2. And you might see you want to be careful with your math because we don't want to miss our 0. Right? So -3. -3 times 2, -6. 11 minus 6 is 5. -3 times 5, -15. -3, look, it's looking good. -3 times 1 is -3. -3 times 12, -36. Woohoo! I found a 0. Remember, we've already found one 0. I'm going to put that over here. Here's one 0 we found. I also just found another 0. And don't forget that I could also be writing this in factored form if it asked me to factor. Then the corresponding factor that goes with the 0, x minus 3, is x plus 3. And so far, then my remaining factor is 2. Let's see. We started out with this being a 4th degree. So this would be 2x cubed plus 5x squared plus x plus 12. And my next step is I'm going to try to factor this thing. Because if I can factor it from right here, I get my other 3 zeros and or factors in one step. But I still can't factor that. So I'm going to go back and just keep trying now my synthetic division on this. Notice what happened. My P's or Q's get adjusted a little bit. P now must be factors of 12. So that lets out the 9, the 18, the 36. Right? So I can down here not check the 9, the 18, the 36, or the 9 halves. I can get rid of those possible zeros. Now remember that last problem had two zeros that were the same number? So when I start my synthetic division, I want to be sure and start with -3 in case there's multiplicity. I don't want to miss it. What if all the zeros are -3? I don't want to miss one. So I don't have to try -1 and -2. I've already shown that they're not zeros. But -3 might have multiplicity. So let's try it again. -3 times 2 is -6. -3 times -1 is +3. -3 times 4 is -12. Yes, I'm glad I did not skip that -3. I just found another zero, and I also just factored this further. I still have these two factors, but now I know that this factor is x plus 3 again, times, now I've worked this down from a cube to a square, so 2x squared minus x plus 4. And once again, once I get my problem worked down to a quadratic, then I'm really done with my synthetic division, because I can either try to factor this. If it won't factor, I can still find my zeros by the quadratic formula or completing the square. In this case, I would need two numbers that multiply to give 8 and add to give -1. Since those numbers don't exist, if the problem were asking me to simply factor that, I would be finished. It doesn't factor any further. But notice I have factored this. Okay, but zeros I'm not finished finding. I've got two zeros in here. So I would go back and continue trying to find these two zeros. We already said it won't factor. It wouldn't be a good one to do completing the square on, so I'm going to do the quadratic formula. Okay, remember that b is -1, so -b plus or minus the square root of b squared minus 4 times a times c all over 2 times a, which is 1 plus or minus the square root of 1 minus 8 times 4 is 32 all over 4, which is 1 plus or minus the square root of -31 all over 4, which is 1 plus or minus I square roots of 31 all over 4. Here are my other two zeros. 1 plus I square roots of 31 over 4 and 1 minus I square roots of 31 over 4. Remember, this rational root theorem only gets rational roots. It doesn't get complex roots. It doesn't get radical roots. So don't keep doing synthetic division. I would not be able to find my other two zeros from synthetic division. Once we get down to a quadratic, we need to shift gears. And here are my 5 zeros that I knew this function should have. Okay, what if we had a question like this that said, find a polynomial function of least degree having only real coefficients with zeros of 2 and 3 plus I. Okay, well, if I have zeros of 2 and 3 plus I, then because of what I know about complex zeros, I also know I have a zero that's 3 minus I. Remember, they occur in conjugate pairs. And if these are zeros, I know that I have corresponding factors of this 0 as x minus 2. And for this one, just imagine, right? Just imagine making this into a 0. So here I would subtract 3 and subtract I, subtract 3 and add I. So my corresponding factors would be x minus 3 minus I and x minus 3 plus I. So there's my function. There it is, f of x. Here is a polynomial that has these zeros. And I can tell it has these zeros because it's factored right here. I need to multiply it out, though, and see what this function is. I'm going to multiply those complex ones out first. So I'll wind up with x squared minus 3x plus ix. Okay, I've multiplied that all the way across, so go to the next one, minus 3x, okay, plus 9, minus 3i, move to the next one, minus ix, plus 3i, minus I squared. Oh, I squared. Remember, anytime we get an I squared, that's really -1. So we have x minus 2. And look, here's a x squared. Here's minus 3x minus 3x. So minus 6x. Here's plus ix, and here's minus ix. So plus ix minus ix. Here's minus 3i plus 3i. And here's plus 9 minus -1. So plus 9 plus 1 plus 10. And then keep multiplying it out. X cubed minus 6x squared plus 10x minus 2x squared plus 12x minus 20. Combine like terms. There's an x cubed. Here's a minus 6x squared minus 2x squared, so minus 8x squared. Here's a plus 10x plus 12x, so plus 22x, and then minus 20. So here is a polynomial function that has these zeros. Okay? Now recall that if I had a graph, and that's a cubic, let's say it has those zeros, not imagine it, let's say 3 zeros. Remember, there's a graph with these 3 zeros. However, there are other functions. What about this one? That has the same 3 zeros. Or what about this one? Has the same 3 zeros. So this is just a function that has those 3 zeros. We could be asked for a specific function with some zeros, like this one. Find a polynomial function of degree 3, which we can tell it's going to be degree 3, with real coefficients that has these zeros and f of 2 equals 30. So I've got a specific other point it has to go through other than just the zeros. But if these are my 3 zeros, then I know that one factor for x equals -3 is x plus 3. The corresponding factor to the 0 x equals 1 is x minus 1. And the corresponding factor to the 0, x equals 4, is x minus 4. Now, here's my function. I haven't multiplied it out yet. But before I do that, and I can do it before or after, but I may want to figure out what particular point this is. It will continue to have these factors. The only difference is, will I have a coefficient in front that I have to multiply that's going to either flip the graph upside down or stretch it or shrink it? So I could say, well, let's plug a 2 in right here. If I just plug a 2 in, let's see what I get. Excuse me. 2 plus 3 is 5. 2 minus 1 is 1. 2 minus 4 is negative 2. So if I plug a 2 in to this function that I found with my zeros, it's obviously not the one they want. So I want to adjust this function so that it continues to have those zeros, but when I plug f of 2 in, instead of equaling negative 10, I want it to equal positive 30. To multiply or divide negative 10 by something to equal positive 30 means I'm going to say negative 10 times negative 3. Negative 10 times negative 3 is positive 30. So if I add a negative 3 to this function that I found with these zeros, it still has these zeros, but now I would have a negative 3 times 5 times 1 times negative 2 when I plug in an f of 2. So here's my function for this one. So multiplying it out, okay, I've got negative 3x minus 9. Just going to go ahead and distribute this one, right? And then I'll multiply these out, 2 at a time, right? So that next one gives me x squared minus 4x minus 1x, so minus 5x plus 4. All right, so continuing to multiply it out, I now have negative 3x cubed. Notice we did get a cube. Plus 15x squared minus 12x minus 9x squared plus 45x minus 36. So simplifying that, combining my like terms, I have negative 3x cubed. Here's 15x squared minus 9x squared. So plus 6x squared minus 12x plus 45x. So plus 33x minus 36. And here's my specific function that has these zeros, but also where f of 2 equals 30. Okay, that wraps up 3.4, I think. It's 4.